we are going to start with alpha particle scattering experiment observations, and how from those observations we have certain calculation by which the Rutherford's atomic model was proposed. So as we have seen in alpha particle scattering, that there were majority of the particles those just passed by without hitting. So you can say that there was absolutely no collision, so particles just pass by like that without any hit. It means that most of the atom is empty. So inside the atom, most of the space is empty. That was what was concluded by Rutherford in this experiment, from this experiment. So, and it said that there are few particles which has kind of scattered more than 90-degree angle. Few, very few. So suppose there is this particle that is coming very close, and then it got scattered in this direction, which is, if this is 90 degrees, so more than 90-degree angle it got scattered. So if you concentrate your study on those particles, you see, suppose if there is some center, and from here this positive helium particles are coming, which is alpha particle. So if this center, which Rutherford have called as nucleus, if the center is positive, then these positive particles get repelled by this center and then get scattered in a backward direction, and more than 90-degree angle they come back, they take a turn and they just reflect back, because there is a high positive charge that it is interacting with, and this is what he has called as nucleus. So there are which type of particle would interact and which type of particle would scattered more than 90-degree, and which type of particle kind of just hit back and hit and just come back at the nucleus. So this whole concept has come from this alpha particle experiment. So suppose I have certain particles, this is its initial direction. From the initial direction, if you take the distance to the center of the nucleus, suppose this distance is small b. This small b is called as impact parameter. Means if your impact parameters are large, then those alpha particle which has the impact parameter very large, they will not get scattered much, because scattering is happening mostly because of the repulsion between these two positive, this centered positive nucleus which has lot of positive charge, and the alpha particles which are coming with a high speed. So there is this very important quantity called impact parameter, which kind of decides as to whether these particles would just pass by or whether it would hit more than 90-degree angle. Or suppose if a particle is coming directly towards the nucleus, which has the impact parameter 0, means there is no distance, it is kind of head-on collision with the nucleus, then this particle or this alpha particle would just return back at 180-degree scattering angle and reflect back, right? So therefore this impact parameter becomes very important, which is the distance of the initial direction of the alpha particle from the center and the nucleus. Now what happens is, when this repulsive force or whatever this force is at the center, suppose there are z amount of charges are there, positive charges, and they have the same electronic charge, which is E, and this alpha particles which has 2e, two electronic positive charge. So when they are coming at a distance r, suppose alpha particle is here, so at a distance r from the center, this would be the Coulombic repulsive force, as we have already studied Coulomb's law. So 1 by 4 pi epsilon naught Ze. Ze is the number of positive charges at the center, into 2e, which is the number of charge of the alpha particle, divided by r square. R square is the distance between them. So this is the repulsive force that starts to get into the picture. So this is the Coulombic force that come into the picture, and as it goes kind of closer to it, it gets repelled so much that it hits back with a high kinetic energy. So therefore this impact parameter is very important. Now talking about the kinetic energy and potential energy, how they play a very important role here. So suppose alpha particle is coming with very high kinetic energy, which is something like 1 by 4 pi epsilon naught Ze into 2e divided by d at a certain distance d. So when it starts coming towards the nucleus, what happens is its kinetic energy starts to kind of reduce, and this kinetic energy starts to convert into the potential energy. So the particle, alpha particle, when it comes very close to the nucleus or the center, the kinetic energy kind of becomes zero and converts totally to the potential energy. But once it is again having this repulsive force, interactive repulsive force, then this repulsive force pushes it back in the opposite direction, and suppose this is a 180 degree, means coming and then going back at the same direction, pushes it back to a very high scattering angle, almost like 180 degree, and then again this potential energy converts into the kinetic energy. So therefore with very heavy kinetic energy, it just moves back, right? So here what we see that when this alpha particle is coming very close to the nucleus, at a certain distance, the kinetic energy becomes totally zero. As we know that it starts with a very high kinetic energy, and as it comes very close to the nucleus, kinetic energy gets slower and lower and lower, and it converts it to potential energy. So potential energy gets higher. So at a certain distance from the nucleus, the kinetic energy becomes zero and the potential energy is very high. So at this point of time, that particular distance where the kinetic energy of alpha particle becomes zero is called, this distance is called distance of closest approach. So this is the closest of the particle that would decide at which angle, because since here the kinetic energy gets totally zero and it's so potential energy, and here whatever is the force and what would be the impact parameter, that decides at which angle the particle would move. Whether if there is hardly any force it feels, then it would just move straight. If the impact parameter is very less, and if it comes very close to the nucleus, then towards the closest approach, it would just feel a very strong repulsive force, and it just bombards it back to 180 degree. So this whole thing plays a very important role, and here we learn about two important things. One is the distance of closest approach, and the impact parameter, which kind of explains the whole system of how this alpha particle is working inside or scattering inside this atom or gold atom. So from here, Rutherford have found that since most of the alpha particles are not coming very close to the nucleus, and they are just not scattering much, and they are just moving away straight without any interaction, so therefore majority of the atom is actually empty. And at the center of this atom, there is all the positive charge that is located, and it must be very high, massive, very, like, most of the mass of the atom is also located at the center, where it is highly positive charges are there, because alpha particles are hitting them and just scattering back with high repulsive force, which is a positive charge, and therefore there has to be a repulsive force between the two positive charges. So therefore the positive charges are centered at the at this nucleus. So he called that, now he said this at this center, this positive charges are centered, and this is called nucleus, and very few alpha particles are deflecting at an angle more than 90 degree, and very few are at more than 180 degree. It means that this nucleus, this size must be very small inside the atom. So at the atom, at the center, it's a very small size, a small volume, where the nucleus is there, where all the positive charges are concentrated, and rest of the atom and majority of the atom is actually empty. There is it's an empty space, there is nothing. So this was concluded, and said he said that the nuclear dimension of the nuclear must be around 10 to the power minus 15 meter to 10 to the power minus 14 meter. So around that, only that amount of space is occupied by nucleus, and rest of the atomic dimension is empty. He also said that since at the center this nucleus is there and rest of the atom is empty, at various circular orbit the electrons are revolving, because this whole thing has to be there, because electrons are negative charge, whereas the whole atom is electrically neutral. So at the center there must be this positive core, which he called as nucleus, and surrounding to it there are these electrons that is revolving. Now why it is revolving, the whole concept comes into the picture. If it wouldn't have been revolving, there must be certain amount of attraction force, and due to that attraction or repulsion force, either electrons would fall on the nucleus, or certain other this balance of force would happen, because we know the Coulombic forces do exist between two charges. So if this is revolving, it means that he says this must be revolving. There is definitely certain Coulombic force acting, but this Coulombic force between the positive charge and the negative charge is providing, this is not due to, this force is not just attracting, and if it would have attracted it would have fallen inside, but it is not doing that. This Coulombic attractive force is providing, or it is using itself as to provide the centripetal force for the electron to revolve around. So the electrons are revolving, for the revolution of electron around the nucleus, you need something called the centripetal force, and this centripetal force is what is sourcing itself from the Coulombic force that is between the charges. So therefore the electrons are neither falling due to the attraction with the positive core, but they are revolving at various circular orbits depending on their Coulombic force and their various distance, and since the radius makes a very important factor here, so at the various circular orbits they are revolving, and their Coulombic force of attraction is used as the centripetal force for the revolution. So therefore this is also a very, very important factor, that we are able to see that electrons are revolving in certain particular orbits, and at the center there is this positive core which has majority of the mass, but it is a very, very small dimension at which all this highly massive positive charges are centered. So this was Rutherford's model of atom, and this whole model has come into the picture just by various observation, analysis of various observation by the alpha particle scattering experiment.
If you like the video, then press the like button, subscribe to the channel and press the bell icon.